Okay, so looking at 50 here, we're going to use completing the square to write the following functions in vertex form, and then find the vertex, direction of opening, the maximum and minimum, and write the domain. So the very first thing that I want to do is actually just look at all three of these. All of these are just quadratics, which means that their domain is just going to be negative infinity to positive infinity for all three of them. Because there's no way that we can get any sort of holes or asymptotes, or excuse me, vertical asymptotes or anything like that. So our domain is just going to be negative infinity to positive infinity for all of these. Okay, so now let's go through, starting with A. We have f of x equals x squared plus 6x plus 5. So to complete the square, we take this number, we divide it by 2, and then we square it. So we're going to have 3 squared, which is 9. So we're going to rewrite this as x squared plus 6x plus 9 minus 9 plus 5. So now, this part here, from here to here, is a perfect square, which means that f of x equals x plus 3 squared minus 4. So this right here is our vertex form, and this means that our vertex is at the negative of this, so negative 3, negative 4 is our vertex. And then because this right here is positive, because this is an implied 1, that means that we open up. And then because we open up, that means our minimum is the y value for our vertex. Okay, for B, we have negative 2x squared, mx equals negative 2x squared minus 10x plus 4. So the first thing we want to do is factor out whatever this coefficient is from all of our numbers. So negative 2 times x squared. So we factor out negative 2 from negative 10, we get plus 5. And then minus 2. So now we take half of this number, then square it. So we get 5 halves squared, which is 25 fourths. So now we take this. This is a perfect square. Oops, 5 over 2. And then I'm going to take this here and distribute it out to these right here. So now we just combine these, and then that's vertex form. So our vertex is at the negative of this point. Sorry, this is a 5 here. So it's at the negative of this point and then this point. And then because this right here is negative, that means we open down. And then because we open down, that means that this value here is our maximum. Okay, last one. g of x equals 3x squared minus 8x. So start by factoring out that 3. So then we're going to take this number here, divide it by 2, and square it. So that's going to be negative 4 over 3. So if we square that, that will become 16 over 9. So now we have so then we take this part here, it's a perfect square. So our vertex form. And then I'm also going to take this and just distribute it out here. So we have this number divided by 2, which is minus 4/3. And then that becomes minus 16 over 3. So this is our vertex form here. Then we open up because that's positive. Our vertex is at the negative of this point and then that point. So positive 4 over 3 and then negative 16 over 3. And then because we open up, we get a minimum at y equals this value here. Okay, 51, we're going to use the vertex formula to find the vertex of the following quadratic functions. So your vertex formula is just going to be that x is going to equal negative b over 2a. And then once you get x, you just plug in x to find your y, and then you can get a point. So starting with a, we have x squared plus 6x plus 5. So b is going to be 6, a is going to be 1, which means that our vertex is going to be negative 6 over 2, or just negative 3. Then we need to find like our y value there. So f of negative 3, if we plug this in, we're going to have 9 minus 18 plus 5. So that comes out to be negative 4. So that means that our vertex is negative 3, comma, negative 4. Okay, now for b, we have a is negative 3, b is negative 9. So x is going to equal, so we have 1, 2, 3 negatives. So negative 9 over 2a, which is 6, is equal to 3 halves. Then we plug this in, not f, g of negative 3 halves. That should come out to be 59 over 4. So that means your vertex is this right here. Okay, now for C, we get that our x location for the vertex, B is 0, which means that our vertex is at x equals 0. So then we just need to find h of 0, which should come out to be just negative 5. So that means our vertex is at 0, negative 5. Okay, 52, a rocket is shot straight upwards from the ground level with an initial speed of 48 meters per second and is modeled using this function here, which represents the height in meters after t seconds. So find when the rocket will reach its maximum height. So because this opens downwards, we know the vertex, that y-coordinate, is going to give us our maximum height as well as the time. So let's find the vertex. So B is 98 and A is negative 4.9, which means that T is going to equal 98 over 2 times 4.9. So this time should come out to be 10 seconds. so that time is t equals 10 seconds. And the height, we just have to take this t and plug it in. So s of 10 gets us 490. Then our units is meters. Okay, now for 53, you're going to have to take this data here and plug it into your calculator using second stat. And then from there, you go ahead and just do calculate the regression. So if you do that, you should end up with the regression that p of t is going to equal negative 0.173 x squared plus 8.312x minus 1.386. Okay, so we have this regression here that we found using our calculator. So now use this model to determine when the population is the greatest and what that maximum population is. And t is in hours. So because this model opens downwards, our vertex is going to give us the maximum. So if we plug this into our vertex formula, we get that t is going to equal negative 8.312 over 2 times negative 0.173. So this comes out to be roughly 24. Then our units are hours. So t equals 24 hours. And then if we take this number here that we got and plug it in here for t, we should wind up with that the maximum population, or p at 24, is going to equal 98,500. Okay, 54, starting with A, we're going to determine the end behavior of the following polynomial functions. So the most important thing for your end behavior is what your highest degree term is doing. So here we can see our highest degree term is this x to the 224. So this is what's going to really dictate all of the behavior, or at least our end behavior. So if we say that x goes to negative infinity, what is our f of x going to do? Well, we have negative infinity to an even power, so that's positive times a negative number, which means that f of x is going to equal negative infinity. And then we're also going to examine positive infinity. So as x approaches positive infinity, f of x is going to go to, sorry. So f of x is going to go to negative infinity. The reason why is because we have this negative right here. So now let's do b. So our highest degree term is at x to the 333. So as x approaches negative infinity, f of x is going to go to, so we'll have negative infinity to an odd degree, which means that we'll have a negative from this here, and then we'll multiply it by negative, which makes that positive. So f of x is going to go to positive infinity. And then as x approaches positive infinity, this one's easy. We know that'll go to negative infinity. For c, our highest degree term is 289. So as x goes to negative infinity, because this is odd, that means that our f of x is going to be negative. And then as x approaches infinity, f of x is going to approach positive infinity. Okay. D, so our highest degree term is 54, which means that as x approaches negative infinity, we look at this one's behavior. So negative infinity to an even power, it's going to be positive times a positive. So f of x is going to be going towards positive infinity. And then same thing for positive infinity. Now for e, we have 2 pi x to the 53. That's our greatest power. And don't let this 2 pi throw you off. Really, that's just a number, right? Pi is just a number. So as x approaches negative infinity, f of x is going to approach, because we have an odd power and no negative out front, it's just going to be negative infinity. And then as x approaches infinity, f of x also approaches infinity. Last one, f, greatest power is this 88 right here. So that one dictates our behavior. So as x approaches negative infinity, because we have an even power, that becomes positive, and then we multiply it by the negative 47, which means that f of x is going to approach negative infinity. And then as x approaches positive infinity, f of x also is going to go to negative infinity. Okay, 55, part A. We're going to find the zeros, state the multiplicities. So generally, if we have some higher order polynomials, generally we want to look for factoring by grouping, which is where we kind of separate the two. So we have g of x equals x cubed plus 7x squared minus x minus 7. So a good indicator here is that we have a 1 and a 7, a 1 and a 7. So that means that we can probably factor by grouping. So if we factor out the largest thing that we can from these two, the largest thing that we can factor is an x squared. So we're going to have x squared, then x plus 7 left. Then we want to make this into an x plus 7, so you can factor out a negative 1. So negative 1, then times x plus 7. So that means that g of x equals x squared minus 1, and then times x plus 7. So if we set this equal to 0, we get that x is going to equal negative 1, 1, and negative 7. And then the multiplicities of all of these is going to be 1, because they're only included once. So even though this here is squared, which gets us these positive and negatives here, the multiplicity is still 1, because the power here is really what's dictating the multiplicity. Okay, moving on to B, we have negative 6x cubed minus 9x squared plus 60x. We're going to set this equal to 0. So notice all these have an x in common, which means that we can factor an x out. We're left with negative 6x squared minus 9x plus 60 equals 0. So now we want to factor this here. So notice all these have a 3, multiple of 3 in them. So we can go ahead and pull that out. And let's actually just go ahead and pull a negative 6 out so we can get a 1 right here. So if we do that, this will be x squared plus 9 over 6 is 3 halves x. Then if we pull negative 6 out from that, we get minus 10 equals 0. So now to solve this, we can go ahead and complete the square. So we can also go ahead and break this apart now and say that x is going to equal 0. It has a multiplicity of 1 because there's no higher degree term here. And then we can go ahead and divide this negative 6 out. And really what we're concerned with now is just this here. So to solve this, we're going to complete the square. So we're going to take 3 halves and divide it by 2 to get 3 fourths. Then we're going to square that. So that's going to be 9 sixteenths. So we get, so we're going to get x squared plus 3 halves x plus 9 sixteenths minus 9 sixteenths minus 10 equals 0. So from here, this will give us the roots that x squared plus 3 fourths or excuse me, not x squared, just x. This squared. Then we're going to have minus 9/16 minus 10 on the outside. We can go ahead and just move that off to the other side. So to combine these two, we just multiply 10 by 16 and make it a common denominator. So we'll end up with 169 over 16. So then we want to take the square root of both sides, and we get that x plus 3/4 is going to equal plus or minus, so the square root of this, 169 is a perfect square of 13, and this is a perfect square of 4. So we get plus or minus 13 over 4. So then we move this 3/4 to the opposite side. We get that we have two roots here with x equaling 10 over 4, which is just 5/2, and that multiplicity is 1. And then x is going to equal, we'll have negative 16 over 4, which is just negative 4. So from here, we have all of our roots, and they're all multiplicity of 1. Okay, for part C, it was fortunate enough to factor all of this for us, which means we know all of our zeros. So we know x equals 0, x equals -3, x equals 2, and x equals -5. So really what we're concerned about is the multiplicity. So for x equals 0, our multiplicity is just going to be 1. So for 0, our multiplicity is 1. Then for -3, our multiplicity is going to be 4, because we have that fourth power right there. For 2, our multiplicity is going to be 3, because we have that third degree exponent right there. Then -5, our multiplicity is going to be 2, because we have that square right there. Okay, 56. Oops. Use the intermediate value theorem to determine if the function has a 0. So the idea behind checking the intermediate value theorem is that if we have some graph, something like this, and we know one point is right here, and one point is right here where we get like a change of sign or something like that, then we know our line, if it's continuous, it just has to cross this axis at some point. There's no way to avoid it. So what we do is we need to find out what those two values are, and if we get a sign change between the two, then that means that we get a 0, or at least 1 0. So start, for A, we're going to plug in f of 0. F of 0 is just going to be -2. Now we plug in f of 1. So f of 1 is going to equal, we will have 1. So because we go from -2 to +1, that means we have to have at least 1 0. So this one is, yes, has 1 0. For G, or excuse me, B, G of x, we do the same thing. So G of 0 is going to equal 15. G of 2, if we plug this in, we should end up getting 27. So because there's not a sign change here, that means that we're not guaranteed to have a 0 between these two. It is possible, it is definitely possible, because we could have something kind of like this here, where up here at 0 we're at 15, and then at 2 we're at 27, and maybe we go something like that. That's definitely possible, but it's not guaranteed. So really what we're worried about is guaranteeing that there is a 0, and here we cannot guarantee it. So no. Last one, h of x, from 1 to 2. So h of 1, if we plug this in, we should go ahead and get 11. H of 2, if we plug this in, we should go ahead and get -10. So because we go from positive to negative, that indicates that we should be guaranteed at least 1 0 between that interval there. Okay, 57. Sketch a rough graph without a calculator or, a graphing function. So we need to do this using the end behavior, zeros, multiplicities of the zeros, as well as y-intercepts. So let's start with the end behavior. So if we plug in positive infinity, this right here is what dictates what our sign is. So positive infinity is going to go up towards infinity. So as x approaches infinity, f of x approaches positive infinity. And then as x approaches negative infinity, f of x, because we have an odd degree, is also going to approach negative infinity. So next we find the zeros. So we're going to set this equal to 0. Start by factoring out an x. Get 0 is equal to x times x squared minus 3. So now we set each one of these equal to 0. So we get x equals 0. We get x squared minus 3 equals 0. So x equals plus or minus the square root of 3. So next we need the multiplicities. All of those are multiplicities of 1, which means that it crosses over the axis and it doesn't just like touch it and then immediately move away. So next we need the y-intercept. So the y-intercept is just whenever x is 0, well, we know x equals 0 is a root, which means that it's also at 0. So our rough sketch for this one, we're going to have something kind of like this. Oops. So we know we should be going towards positive infinity and then negative infinity. We know that we should have a root here at negative root 3. We should have a root here at 0. We should have a root here at root 3. So we can imagine then that our graph is going to go something maybe kind of like this, like that. It's pretty rough. We don't need the exact values. That's good enough. Okay, then we're going to do the same thing we just did for 58. So to aid in sketching the function, find end behavior. So the end behavior, we can see that if we kind of multiply all these out, we get that we're going to have an x squared from here times an x cubed, and then a positive here. So we get something maybe like our largest term should be 2 times x to the 5th, which that dictates our behavior. And because that's odd, that means that as x approaches negative infinity, our y is going to go to negative infinity. And then as x approaches positive infinity, y is going to go to positive infinity. So the zeros, we already know. There's a 0 at x equals 1 with a multiplicity of 2. There's a 0 at x equals negative 1 with a multiplicity of 3. And then there is our y-intercept. So to find our y-intercept, we plug in 0. So if x equals 0, our y is going to equal, we'll have negative 1 squared, which is 1, times 1 cubed, which is just 1, times 2. So that y value is 2. So now, if we go ahead and try and sketch our graph, so we know as negative infinity, as x approaches negative infinity, we go towards negative infinity, and then positive infinity. We know at 0, we have some point here, 0, 2. We know we have a 0 at x equals 1, and a 0 at x equals negative 1. So we know the multiplicity at negative 1 is 3. So because that's odd, what that means is that it's just going to cross right through it. So we might have something kind of like this. We know that we cross here, so maybe we come back now. And then because our multiplicity at that root 1 is even, or 2, that means it's just going to kind of bounce off of it like that and go towards infinity. So it's a little rough, again, but it's fine. Good enough. We got the features that we want, which is those zeros, the y-intercept, and the end behavior. That's really, and then the general shape. That's really good enough for what this question wants. Okay, 59, starting with A, we're just going to do some long division here. So we have, inside, we have 6x cubed minus 5x squared minus 3x plus 4. We're dividing this by 3x plus 2. So we're only focusing on this and making this line up with that. So what times this will equal that? If we multiply 3x by 2x squared, we get 6x cubed plus 4x squared. And then we subtract this off. So what that gets us is 0 here, and then negative 9x squared. Then next we bring down that minus 3x. So next we do what times 3x will get us this. That's going to be negative 3x. So if we multiply this out, we get negative 9x squared, and then minus 6x. Then we make this negative. So these will cancel out. Then we'll get 3x plus 6x, or excuse me, negative 3x plus 6x, which is going to be 3x. So then we actually just have plus 1 to make, because we can multiply this into this. And then we also, at the same time, need to bring this 4 down. So if we do that, now we have 3x plus 2. We make this negative, and we're left with 0 and then 2. So that means that our answer is 2x squared minus 3x plus 1 plus, we have our remainder here of 2 divided by this. 2 over 3x plus 2. Okay, now for b, we're going to divide 3x to the 4th plus 2x cubed plus 4x squared plus x minus 5 by x squared plus 2. So we start, what times x squared will get us to here? That's 3x squared. So if we do that, we get 3x to the 4th, and then plus 6x squared. And what we notice here is that these don't actually line up. So what that means is we're going to take this, and we're going to put 0 here, plus 6x squared. And really, what we could have done is right at the start, we could have just wrote this in this form here, where we have x squared plus 0x. So that way it's more apparent that we get that 0 there. So now we divide these out, we make this negative. So that cancels. And then we have 2x cubed. And then 4x squared minus 6x squared is minus 2x squared. And then we can go ahead and bring down that x and that negative 5. So now, what times x squared gets us to this? That's going to be 2x, so plus 2x. So we get 2x cubed plus 0, and then, oops, earlier this was supposed to be plus 2, and then 4x. Then we make this negative. So those cancel out. We bring down that negative 2x squared. And then x minus 4x is going to be minus 3x. We bring this 5 down. So now, what times x squared gets us to this? That's just negative 2. So then we have negative 2x squared minus 0. And then minus 4. So then we make this negative, right? So then we get 0 minus 3x, and then we have negative 5 plus 4, which is negative 1. So we can no longer take this and put it into here. So we're all done, and this is our remainder here. So our answer is 3x squared plus 2x minus 2, and then we have minus 3x minus 1 divided by x squared plus 2.
Use synthetic division to divide the following polynomials. Give the answer as quotient plus the remainder divided by the divisor. Show all work. So we'll take the coefficients there. So that'll be 1, 3, -1, 7, and 2. And then we are going to solve for the 0 there, which will be a positive 3. Bring down the 1. 1 times 3 is 3. 3 plus 3 is 6. 6 times 3 is 18. -1 plus 18 is 17. 17 times 3 is 54. Correction, 51. 7 plus 51 is 58. 58 times 3 is 174. Leaves us with 176 as the remainder. So then we can rewrite this with the powers reduced by 1. So we would get x cubed plus 6x squared plus 17x plus 58 plus 176 over our x minus 3. Part B. So we're going to do the same thing, but we actually have missing x to the power terms. So we're going to have to put zeros in there when using synthetic division. So we'll start with the highest, 2 x to the 5th, and then this will 0 be x to the 4th, 0 x to the 3rd, x to the 1st, or sorry, x to the 2nd, my apologies, is 1, minus 5, 1, and we are dividing by x minus, or x plus 2, so it'll be a minus 2. So carry this one down. 2 times -2 is -4. 0 plus -4 is -4. -4 times -2 is positive 8. 0 plus 8 is 8. 8 times -2 is -16. 1 plus -16 is -15. -15 times 2 is positive 30. -5 plus 30 is positive 25. And 25 times -2 is -50. So we're left with -49. And then just like before, we're going to rewrite this, except with a reduction in power. So this will be 2x to the 4th minus 4x cubed plus 8x squared minus 15x plus 25, and then plus, we'll do the remainder of -49 over x plus 2. 61. Use remainder theorem to evaluate the polynomial f of x is equal to 3x to the 4th plus 2x squared minus 4x plus 1 at f equals -2. So we'll again be using synthetic division. So we'll set that up with the coefficients of 3, and then we don't have an x cubed term, so there's a 0, plus 2, minus 4, plus 1, and then we are evaluating this at -2. So drop 3 down. 3 times -2 is -6. 0 plus -6 is -6. -6 times 2 is 12. 2 plus 12 is 14. 14 times -2 is -28. -4 plus -28 is -32. -32 times 2 is positive 64. 1 plus 64 is 65. And the remainder theorem states that what's ever left over here is the function. So f of negative 2 is equal to 65. 62, use remainder theorem to determine if negative 5 or 2i are zeros of the polynomial of f of x equals x to the fourth plus 6x cubed plus 9x squared plus 24x plus 20. Show all work. So let's first check if negative 5 is a 0. So we have 1, 6, 9, 24, and 20. And we'll check negative 5 first. So we get 1. 1 times negative 5 is negative 5. Come down to 1. 1 times negative 5 is negative 5. 9 plus negative 5 is 4. 4 times negative 5 is negative 20. 24 plus a negative 20 is 4. 4 times negative 5 is negative 20. And we get a 0. So in fact, negative 5 is a 0. Now we could do this exact same procedure for the 2i, or we can take the remainder coefficients and use those to determine if 2i is in fact a 0. So drop the 1 down. 1 times 2i is 2i. So now we get 1 plus 2i. 1 plus 2i will give us 2i, 1 plus 2i, so that'll be 2i plus 4i squared. I have 2i minus 4. So this will be 2i minus 4. Add them together, we're left with 2i here. 2i times 2i will result in negative 4, and we'll get a 0. So yes, both negative 5 and 2i are zeros. Use the factor theorem to determine if x plus 3 or x minus 3i are factors of the polynomial of f of x equals x cubed plus 4x squared plus 9x plus 36. Show all work. So this is again going to be synthetic division. We'll check the real one first. So that will give us 1, 4, 9, 36. We're going to take the opposite sign. See if we get a 0 from this. So 1 times negative 3 is negative 3. We'll get 1. 1 times negative 3 is negative 3. We'll get 6. 6 times negative 3 is negative 18. And that will be a positive 18 as a remainder. So x plus 3 is not a factor. So now we can try the 3i. And since this did not zero out, we will have to use these original coefficients. So we flip the sign of 3i, or we would say x minus 3i equals 0, so x has to equal 3i. So 3i, 1, 4, 9, 36. So drop the 1 down. 1 times 3i is 3i. So we get 4 plus 3i 3i times 4 plus 3i will give us 12i minus 9. So 12i minus 9 will give us 12i here, and that would be 36i squared, or negative 36, and we get a 0. So x minus 3i is a factor. Find all the zeros of the function f of x is equal to 4x cubed minus 20x squared plus 33x minus 18, given 2 is a 0. Write the function as linear factors, show all work. So given that we are already given a 0 in the problem, we might as well reduce that polynomial, make it a little bit easier on ourselves. We'll just go ahead and use synthetic division, but if you knew how to get the factor, you could also use polynomial division. So 4 times 2 is 8, negative 12, negative 24, get positive 9, 9 times 2 is 18, leaving us with a 0. So now we can rewrite that polynomial after it's been reduced as x minus 2, or the factor that we had, and now we have 4x squared minus 12x plus 9. At this point, we could go through possible rational roots, or we could just find the zeros of this using the quadratic formula, or we could even factor. I'm not seeing any particularly easy factors, so I'm going to use the quadratic formula. Minus 4ac. So the quadratic formulas are negative b plus or minus the square root of our b squared minus 4 times our a term, which is 4, times our c term, which is a positive 9. All of this over 2 times our a term, which is 4. We get 12 plus or minus 144 minus 144 all over 8. So this will be 12, it'll be a little odd here, plus or minus 0 over 8, which reduces down to 3/2 plus or minus 0. So the reason we kept this right here is we should expect 2 zeros to come about it. Because only one value popped up, that means that this is a repeated root. So the zeros are going to be the 2 they gave us, and then 3/2 and 3/2. Or we could say 3/2 multiplicity 2 and 2. Continuing on, I erased everything, but I just noticed that it said you should write them as linear factors as well too. So that would be f of x is equal to x minus 2, the factor that they gave, x minus 3/2, x minus 3/2. And then usually we'll simplify this. would be 3/2 squared. Write a polynomial p of x of degree 3 in standard form with zeros -5, √2, and -√2. Show all work. So we can set that up as p of x is equal to x plus 5, x minus √2, x plus √2. I'm going to combine these two. For those of you who notice, this will be a difference of squares to that, but we will show the expanded form out. So we'll get x squared plus √2 times x minus √2 times x minus two. P of x will be x plus 5, x squared, those two will cancel out, minus 2, which will make the math a little bit easier when combining these two. So we'll get x cubed minus 2x plus 5x squared minus 10. Now that's not quite in standard form because we want it decreasing in power. So x cubed plus 5x squared minus 2x minus 10. And that is indeed a degree 3 polynomial with those zeros. All right, question 66. Find all the zeros of the polynomial f of x is equal to x to the 5th plus 3 times x to the 4th plus 14x cubed plus 42x squared minus 32x minus 96. Given that -3 and 4i are zeros. Show all work. So, a few ways to approach this. Because we weren't given a specific method, we can use polynomial division or synthetic division. I will be using a combination of both. And also, given that we are given a positive 4i as a 0, we automatically know that -4i is also a 0. So let's use synthetic division for that first real 0. So we'll do 1, 3, 14, 42, -32, -96. So 1, -3, 0, 0, 14, 14 times -3 is -42, which is 0, 0, -32. -32 times that is a positive 96. And in fact, we do have a 0. We can then rewrite this as a degree less. So we'd have x to the 4th plus 0x cubed plus 14x squared minus 32. Now here's the trick that I'll show with the imaginary zeros. So the roots of that are going to be x minus 4i and then the conjugate x plus 4i. And where we all multiply this all out, we're going to get x squared plus 16. So we can use this in the polynomial division, and we'll get both of those roots factored out at the same time. So what do we have to multiply x squared by to get x to the 4th? x squared. So this will be, then we multiply by over here, so we get x to the fourth plus 16 x squared. And we'll subtract that off. So we'll get 0, which is what we're hoping for, minus 2x squared. What do we have to do to get 2x squared out of this? We would multiply that by a negative 2. So then we would get minus 2x squared minus 32. I can do this. And then we're going to subtract that off, 0 and 0. And so we're left with x squared minus 2. At this point, we're trying to find zeros, and since we don't have that middle term, we can just solve directly for x. Okay. So now we can list all the zeros. So they gave us negative 3 and 4i. From that we got the conjugate of the imaginary, so negative 4i, and then we solved for positive root 2 and then negative root 2.